Hello everybody, this is Dr. Pennington again, and I am going to talk to you about two fundamental chemical laws today that go part way to describing why elements bind the way they do to form compounds. First off is something called a law of definite proportions, and this one's a little easier to describe than the second one, which is the law of multiple proportions. So we'll look at this one first. This was first discovered by a chemist by the name of Proust all the way back in 1797. So this has been around for a long, long time. This has been a known fact for, well, like I said, a long time. And let's just start off with a nice simple analogy here. Just think about let's think about a very common molecule that we see everywhere, and that very common molecule is water. All right. Think about the water that you have, say, in your water bottle on your desk, or the water in your toilet cistern, or the water inside your body, or the water found in a stream in Iceland, or the water found in a bottle of Coke, or the water found in a gallon of, well, whatever, a bottle of beer or a bottle of vodka. You know, the fact is, all that water is, you know, it's still water, it's just in different situations. The question is the water the same in each case? Well, of course it is, otherwise it wouldn't be water. The idea being that water is defined by this ratio of atoms here. 2 atoms of hydrogen to 1 atom of oxygen. That's what defines water. Is this water? Well, no, because we've got 3 hydrogens to 1 oxygen. Is this water? Well, exactly the same reason, no, because we don't have 2 hydrogens to 1 oxygen. All right. The actual law of definite proportions is actually can actually be related to the masses of the elements involved, and let's just talk about that right now. What the law says is that all samples of a given compound, that given compound being water in this case, regardless of where they come from, regardless of their origin, always have in the same proportions the masses of their constituent elements, which in this case is hydrogen to oxygen. All right. The fact is, in every single molecule of water, you'll see a mass ratio of 8 grams of oxygen to 1 gram of hydrogen. All right, and that ratio is just an absolute given for water. Otherwise, it's not water; it's something else. This doesn't say go. This says grams of oxygen. Okay, and so to explain why this is the case, we've got to look at the actual formula. The atomic mass of hydrogen is essentially 1 gram per mole. The atomic mass of oxygen is 16 grams per mole. Now, if we have these atomic weights, you can see that oxygen is 16 times bigger than hydrogen. So that should give us a ratio of 16 to 1. So why is this mass ratio 8 to 1? Well, of course, it's because there are 2 hydrogens there, and when we have 2 hydrogens, what that really means is, because we've got 2 hydrogens, that's 2 grams per mole, versus 1 oxygen, which is 16 grams per mole, and of course that collapses down to 2 over 16, or 16 over 2 is the same thing as saying 8 over 1. So that means 8 grams of oxygen to 1 gram of hydrogen. Exactly the rule that we said here. The law of definite proportions is true for every sample of every molecule that's the same as whatever you are looking at. So every sample of water always has the same ratio of oxygen and hydrogen in it, otherwise it's not water. Alright. Let's just do the same thing for, let's have a look at carbon dioxide, for example. Okay, CO2. Every sample of CO2 has exactly the same mass ratio of carbon to oxygen. All right. 44 grams of CO2 decomposes to 12 grams of carbon and 32 grams of oxygen. All right. And we can come up with a mass ratio of our atoms here. we can simply say 32 grams of oxygen to 12 grams of carbon, and we just divide this out. Now here's a challenge for you. Let's see who can do this without using a calculator. 32 divided by 12. Well, let's see. 32 and 12, they can both be divided by 4, so that gives us 8 over 3. And when we do that, then that gives us 2 and 2/3, which is the same thing as saying when you punch it into your calculator and you get 2.667. So what that means is for every 2.667 grams of oxygen, we have 1 gram of carbon. Alright, so that mass ratio of oxygen to carbon is 2.667 to 1, or 2.67 to 1, however you want to say it. So here's a question for you. We had 2 samples of CO2. Alright? 2 samples of CO2. One sample produced 25.6 grams of oxygen and 9.6 grams of carbon. The other sample produced 21.6 grams of oxygen and 8.10 grams of carbon. And the question is, show that these results are consistent with the law of definite proportions. Okay? All we have to do here is then do what we've done down here. If these are both CO2, then when we divide both these out, we should get this same ratio. If we don't, what that tells us is these samples are not the same. They're not both CO2. So for sample number 1, we know we've got 25.6 grams of oxygen, and at the same time we get 9.6 grams of carbon. And if we divide that out, I will use my calculator for this, 25.6 divided by 9.60 gives me a ratio of 2.67 to 1. Alright? Which, not surprisingly, is the same as what I got down here. Then I'm going to do the same for sample number 2, 21.6 grams of oxygen, 8.10 grams of carbon. I do the same thing here, 21.6 divided by 8.10 gives me, again, 2.67 to 1. So the idea is, both of these fit the law of definite proportions because they both have the same ratio. And they both have the same ratio that we know is true for CO2. So that is the law of definite proportions and how we can predict if compounds fit it. Now for the law of multiple proportions, we've got to be a little bit more careful in the description of what's going on, and let's just be careful about it. This was first described by a chemist by the name of John Dalton in 1804. So over 200 years ago, this Dalton guy was pretty prolific. And so what he said, and I'm just going to read this law out and then we'll go through an example of it. When you have 2 elements, for example carbon and oxygen, when these 2 elements form 2 different compounds, assuming those 2 elements do form 2 different compounds, and I think everybody knows that CO2 is one compound of carbon and oxygen, carbon dioxide. Carbon monoxide is another one. They're both made of carbon and oxygen. So when 2 elements form 2 different compounds like these 2, the masses of, for example, oxygen that combine with 1 gram of carbon can be expressed as small whole numbers. Now that might be a little bit confusing, and let me just explain it by going through an example here. We saw before for carbon dioxide the ratio of carbon to oxygen was 2.67 grams oxygen to 1 gram of carbon. Alright. So we said 2.67 grams of oxygen to 1 gram of carbon. If this law of multiple proportions is true, when I do the same thing for carbon monoxide, I will get a certain ratio of grams of oxygen to grams of carbon, and these grams of oxygen should be small whole numbers. These should be in a ratio of small whole numbers. Now let me just actually see if that's the case. Remember, we got this 2.67 by saying that in CO2 we have 32 grams of oxygen to 12 grams of carbon. And 32 divided by 12 gives us 2.67. Now in carbon monoxide, we don't have 32 grams of oxygen, we only have one atom of oxygen, so therefore it's 16 grams of oxygen to 12 grams of carbon. Notice the number of grams of carbon stays the same because the number of atoms of carbon stays the same. If we divide through by 12, we get 1 gram of carbon, and 16 divided by 12 gives us an answer of 1.33 grams of oxygen. So this is our ratio. Here the ratio is 2.67 to 1, here it's 1.33 to 1. The important information here is these numbers here. Do these exist in the ratio of a small whole number, assuming these two are the same? And in this case, they do. Alright, if I just write out the mass of oxygen to 1 gram of carbon in CO2, and then underneath that I put the mass of oxygen to 1 gram of carbon in CO, I know that's 2.67 grams from CO2, it's 1.33 grams for CO, that divided by that gives me 2. Because this number is a small whole number, that means that these two compounds fit the law of multiple proportions. Now hopefully that makes sense, because this can be a kind of tricky thing to understand. Let's do one more example of that with a couple of different elements. In fact, the elements we're going to use are nitrogen and oxygen. Alright. So it turns out that nitrogen forms several compounds with oxygen. And one of those is nitrogen dioxide, and another one is dinitrogen monoxide. Now our nitrogen dioxide contains 2.28 grams of oxygen to every 1 gram of nitrogen, whilst in the dinitrogen monoxide we have 0.570 grams of oxygen to every 1 gram of nitrogen. The question is, show that these two compounds fit the law of multiple proportions. Well, actually most of the work is done for us at this point. The 1 gram of nitrogen is set, those are fixed, and all we've got to do is to see, do the amounts of oxygen here, do they divide out to give the ratio of a small whole number? So when we take the mass of oxygen in NO2 per 1 gram of nitrogen, we've got 2.28 grams. I'm doing exactly what I did back here right now. So the mass of oxygen to 1 gram of nitrogen in NO2 is on the top. The mass of oxygen to 1 gram of nitrogen from N2O is on the bottom. It's grams of oxygen. And so hopefully, if this is right, if I divide these out, so 2.28 divided by 0.570, I should, cross fingers, get a small whole number. And I do. The answer is 4. So what that means, that's an exact small whole number. Therefore, the results are consistent with the law of multiple proportions. Alright? Bear in mind, I could have done exactly the same question if I hadn't started from these ratios, if I'd started from the actual masses of elements involved. I could have said, I've got 2 oxygens in my NO2, so that means 32 grams of oxygen to 14 grams of nitrogen in my NO2. And in my N2O, if I've got 2 nitrogens, I've got 28 grams of nitrogen, 16 grams of oxygen. what you'll find is with these numbers, this is kind of like what we had here. We got from these numbers to here by dividing through by the smallest number in each case. And it's exactly the same here. If I divide both of these through by 14, I get to these numbers here. If I divide both of these through by, actually by this case in 28, because I want to make sure the nitrogens are 1 in each case, I get these numbers here. So you can start from two different places potentially and get to the same answer. So that's the law of multiple proportions. We've already talked about the law of definite proportions, and we are done. Thank you.